Imagine standing outside on a clear night, far from any city, far from any light pollution, and just looking up. The sky above you is not empty. It never was. Every single point of light you can see with your naked eye is a sun, a burning, churning, violent engine of nuclear fire, some of them so enormous that if you placed one at the center of our solar system, its outer edge would swallow Jupiter whole. And every single one of those stars, without exception, will die. That is one of the most fundamental truths of the universe we live in. Everything that burns eventually goes out. Physics demands it. Thermodynamics insists on it. Even the oldest stars, the ones that have been fusing hydrogen in their cores since the universe was young and cool and just beginning to understand itself, even those ancient titans are counting down toward an inevitable end. But here is where the story gets strange. Here is where the universe, for all its cold indifference, does something that feels almost like defiance. Some stars do not go quietly. Some stars do not simply exhaust their fuel, collapse inward, and fade into the dark like a candle drowning in its own wax. Some stars explode. They explode with a violence so total, so absolute, so catastrophically brilliant that for a few weeks they outshine entire galaxies containing hundreds of billions of other stars. We call these explosions supernovas, and for a long time we thought we understood them. We thought we had the basic story figured out. A star lives, a star dies, a star explodes. End of story. We were wrong. Because some of these stars, and this is where everything changes, this is where the familiar story cracks open and reveals something underneath that nobody expected. Some of these stars explode and then refuse to stay dead. They erupt once, cool down slightly, and then erupt again. Some of them have been caught brightening and dimming in patterns that suggest repeated explosions separated by years or even decades. Some of them seem to have shed enormous shells of material before the main event, as if they were rehearsing their own destruction. Some of them produce afterglows that last not for weeks or months, but for years, burning with a stubbornness that contradicts every model astrophysicists had built. Scientists, searching for a name that captured the nature of what they were seeing, called them zombie stars. Supernovas that refuse to die. Ask yourself this right now, at home, in your chair. What does it mean when even the death of a star does not follow the rules? What does it mean when something that should be finished, that should be over, that should have gone dark and cold and quiet, keeps coming back? And what does it tell us about the universe itself, about the nature of energy and matter and time, when the most violent event we know of turns out not to be a single moment but a prolonged, agonizing, magnificent refusal? This is the story of zombie stars. And it is not a simple story. It is not a story with clean edges and comfortable conclusions. It is a story that begins in the early universe and stretches to the present day. A story that has confused the world's greatest astronomers, forced the rewriting of textbooks, revealed entirely new classes of stellar objects, and raised questions so profound and so unsettling that some of the smartest people alive spend their entire careers just trying to frame them correctly. It is a story about the outer limits of what we understand, about the moments when the data says something impossible and the scientist staring at the data has to decide whether the instrument is broken or whether the universe just did something nobody thought it could do. It is a story about physics pushed to its absolute breaking point. And it is a story, in the deepest sense, about what it means to refuse to end. To understand zombie stars, you first have to understand the life of a normal star, because you cannot appreciate the aberration without understanding the rule it breaks. A star is born from a cloud of gas and dust, an enormous nebula drifting through space, pulled together by its own gravity over millions of years. As the cloud collapses inward, it heats up. The atoms in the center are squeezed closer and closer together until something remarkable happens. The temperature and pressure reach a threshold, and hydrogen nuclei, single protons, begin to fuse together. Two protons slam into each other with enough force to overcome the electromagnetic repulsion that normally keeps them apart, and they merge, and in merging they release energy. That energy is sunlight. That energy is warmth. That energy is, in a very real sense, life. Our entire biosphere, every animal, every plant, Every microorganism that has ever lived on this planet exists because of nuclear fusion happening in the core of our star. And for a while, sometimes a few million years, sometimes a few billion years, depending on the size of the star, fusion keeps the star in balance. It is a delicate equilibrium, actually a profound tension between two forces that could not be more different. Gravity is always pulling the star inward, trying to crush it, trying to collapse it down to a single point. And the energy released by fusion is always pushing outward, trying to expand the star, trying to blow it apart. As long as there is fuel to burn, these two forces hold each other in check. The star glows. The star endures. The star is, in the most fundamental physical sense, alive. But stars are not conservative with their fuel. They burn hot and they burn fast. Our own sun, which is a relatively modest middle-of-the-road star by cosmic standards, converts about 600 million tons of hydrogen into helium every single second. Every second. And it has been doing this for about 4.6 billion years. The numbers involved in describing stellar physics are so extreme that the human brain genuinely struggles to hold them. When we talk about a star burning 600 million tons of anything per second, we are not talking about something we can picture. We are talking about numbers that live beyond intuition, in the territory of pure abstraction where mathematics is the only language precise enough to describe what is happening. So what happens when the fuel runs out? When a star like our Sun exhausts the hydrogen in its core, it cannot maintain the balance. The core begins to contract under gravity, heating up further, until the temperature is high enough to fuse helium instead. As helium fuses into carbon and oxygen, the star's outer layers expand enormously. The star becomes a red giant, ballooning outward in a final act of expansion before the inevitable. And when even the helium runs out, for a star of our Sun's size, the outer layers drift away into space as a beautiful nebula, and the core collapses into a white dwarf, a dense, hot remnant about the size of the Earth, made almost entirely of carbon and oxygen, slowly cooling over billions of years until it becomes a cold, dark object called a black dwarf. Though it is worth noting that the universe is not yet old enough for any white dwarf to have cooled all the way to a black dwarf. Every white dwarf that has ever formed is still cooling. The universe is still too young for its dead stars to have gone completely dark. Now, that is the story for a star like ours. A relatively quiet death. Poetic, even. A gradual expansion, a slow exhale of material, a cooling remnant. But for stars much more massive than our Sun, stars 8 times more massive or greater, and sometimes far, far more massive than that, the death is not quiet at all. For massive stars, the end comes not as a slow sigh, but as a catastrophic, universe-shaking explosion. And to understand why, you need to understand something about what happens inside a massive star during its life. A massive star does not simply fuse hydrogen into helium and stop there. Because of its greater mass and therefore greater gravitational pressure and greater core temperature, it can fuse progressively heavier elements. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and silicon ultimately into iron. Iron. And this is where everything changes, because iron is what astrophysicists call the end of the nuclear road. Iron is the most stable nucleus in the periodic table. To fuse iron requires more energy than the fusion releases. You cannot get net energy out of fusing iron. You cannot use iron as a fuel. So when a massive star builds up an iron core, when silicon fusion in the core produces more and more iron until the iron core grows to about 1.4 times the mass of our Sun, a critical threshold called the Chandrasekhar limit, fusion stops. And without the outward pressure of fusion, gravity wins instantly and completely. The iron core collapses in less than a second, in fractions of a second. The core, which was the size of the Earth, collapses down to a ball roughly 20 kilometers across. The density of this newly formed neutron star, because that is what the core becomes, a neutron star, a ball of matter so dense that its protons and electrons are forced together to form neutrons, is almost incomprehensible. A teaspoon of neutron star material would weigh about 10 million tons on Earth. Let that sit with you for a moment. A single teaspoon. 10 million tons. The entire mass of the original iron core, which might have been 1.4 solar masses, crushed into a sphere 20 kilometers across in less than a second. The collapse happened so fast that the outer layers of the star, still falling inward, do not even have time to react. They fall, they hit the newly formed neutron star, and the resulting shockwave bounces back outward with unimaginable force. This is the supernova. The shockwave tears through the outer layers of the star, accelerating them outward at speeds of thousands of kilometers per second. The star brightens explosively. Within hours, it becomes one of the most luminous objects in the observable universe. A single supernova can outshine a galaxy containing hundreds of billions of stars. The energy released in a supernova is staggering, roughly 10 to the power of 44 joules, which is more energy than our sun will release in its entire 10 billion year lifetime. And 99% of that energy, astonishingly, is carried away not by light but by neutrinos, ghostly subatomic particles that barely interact with matter at all, that pass through the entire bulk of the Earth as if it were not there, that are streaming through your hand right now in unimaginable numbers from every direction in space. Now here is the question that gets to the heart of everything this story is about. Ask yourself this: if a supernova is that powerful, if it represents the complete and total destruction of a massive star, if it releases the equivalent of the sun's entire lifetime energy output in a matter of seconds, then what could possibly cause it to happen twice? What mechanism, what physical process, what extraordinary circumstance could cause a star to survive its own supernova, only to explode again? What kind of universe allows for that? And yet, in 2014, astronomers studying archived data from the Palomar Transient Factory, a survey designed to detect changing and transient objects in the night sky, noticed something deeply unusual about a supernova designated IPTF-14HLS. When it was first detected, it was classified as a hydrogen-rich supernova, called a Type II supernova, and nobody was particularly alarmed. Type II supernovas happen. They are well understood. They have a characteristic light curve, a pattern of brightening and dimming over time, that astrophysicists have measured hundreds of times and can predict with reasonable accuracy. Typically, a Type II supernova reaches peak brightness and then dims steadily over a period of weeks to months. It follows the curve. It behaves. It dies. IPTF-14HLS did not behave. Instead of following the expected light curve, IPTF-14HLS brightened and dimmed at least 5 separate times over a period of 600 days. 600 days. Nearly 2 years of repeated brightening and dimming from what should have been a single, finite explosion. Astronomers at Caltech and the Las Cumbres Observatory began studying it intensively, and what they found in the spectral data, the light broken into its component wavelengths, a technique that tells you what elements are present and how the material is moving, made them rethink everything they thought they knew about stellar death. The supernova showed velocities in the expanding material that were far higher than expected for such a long-duration event, suggesting not one explosion but multiple ejections of material at different times. And then they found something even stranger in the archival data. Looking back through old photographic plates from the Palomar Observatory Sky Survey taken in 1954, astronomers found evidence of a brightening at the exact location of IPTF-14HLS, 60 years before the supernova that was being observed in 2014. In 1954, 60 years earlier, something had exploded at that location 60 years before what everyone thought was the main event. The star had, it seemed, undergone a massive eruption in 1954 and somehow survived. And then it exploded again in 2014, and then it kept exploding over and over, brightening and dimming 5 times across nearly 2 years. The paper describing these findings, published in the journal Nature in 2017 by Yair Arkavi and colleagues, created an immediate sensation in the astrophysics community. The authors themselves called IPTF-14HLS the most peculiar supernova ever observed. Not unusually energetic, not chemically strange, the most peculiar, the most confounding, the most resistant to explanation. And the question that hung in the air after that paper was published, the question that is still being debated today, is, what could possibly explain this? Here is where the theories begin, and it is important to be clear that what follows involves real scientific speculation, the kind of rigorous, evidence-based speculation that pushes physics toward its own frontier. These are not fringe ideas. They are serious proposals from serious scientists, and they demonstrate just how strange and poorly understood the deaths of massive stars still are, even after decades of observations and calculations. One of the leading theoretical explanations for objects like IPTF-14 HLS is a mechanism called pulsational parent stability. And to understand what pulsational parent stability is, you have to go even deeper into the physics of massive stars. The most massive stars in the universe, those with initial masses perhaps above 100 times the mass of our Sun, and sometimes several hundred times more massive, undergo a process in their cores that less massive stars never experience. At the extreme temperatures in the cores of these stellar giants, photons, particles of light, carry so much energy that they can spontaneously create pairs of electrons and their antimatter counterparts, positrons. This process, called pair production, actually reduces the radiation pressure in the core because the photons are being converted into matter instead of pushing outward. When the radiation pressure drops, gravity momentarily overcomes the outward force, and the core begins to collapse. But here is what makes this different from the final collapse of a normal massive star. In a pulsational parent stability event, the collapse does not go all the way. The compression heats the core so intensely that explosive nuclear burning begins. A sudden, violent burst of thermonuclear energy, and the energy released is enough to reverse the collapse. The star does not implode. Instead, it rebounds, and the rebound ejects an enormous shell of material into space. The star survives, for now. But the ejection does not stabilize the star permanently. It has lost mass, changed its internal structure, and the processes that led to pair instability are still operating. So the core can contract again, and the same thing can happen again. The star collapses, burns, rebounds, ejects material, and this can repeat, potentially many times, each explosion ejecting another shell of material into the space around the star. Each ejection is itself a massive explosion, what astronomers call a pulsational parent stability supernova, or PISN, event, but the star survives each one, until finally the star has either lost enough mass or undergone enough disruption that the final collapse happens. A true, terminal supernova that destroys the star completely. The visual result of this process, as seen from Earth, would be a source of light that brightens and dims repeatedly, with each pulsation corresponding to a new ejection event. If the ejected shells of material from earlier pulsations are still in the vicinity when a later pulsation occurs, the expanding material from the new explosion slams into the old shell, producing an additional burst of light as kinetic energy is converted to radiation. The bumps in the light curve of IPTF-14 HLS could be explained by exactly this mechanism, each bump representing either a new pulsation or the interaction of expanding material with a previously ejected shell. But there is a problem, and the problem is the mass. Pulsational parent stability is predicted to occur in stars with initial masses above approximately 100 solar masses. These are the most massive stars in the universe. Rare, extreme objects that burn their fuel furiously and live short, spectacular lives. If IPTF-14 HLS was a pulsational parent stability supernova, then the star that produced it would have needed to be extraordinarily massive. And when astronomers tried to model the progenitor star of IPTF-14 HLS using all the available observational data, they found that while pulsational parent stability could explain some features of the event, it could not fully account for all of them. The light curve had the right shape in some ways, but the wrong timescales in others. The velocities of the ejected material were higher than some models predicted. The total energy of the event seemed, in some estimates, too large even for a parent stability event. which means either the models are incomplete, which they almost certainly are, because stellar physics at these extremes is genuinely at the frontier of what can be calculated, or something else entirely is going on. And this is the extraordinary thing about IPTF-14 HLS and objects like it. They are not just strange observations. They are diagnostics of our own ignorance, windows into the gaps in our understanding of one of the most fundamental processes in the universe. Every time an astronomer stares at the light curve of IPTF-14 HLS and says, "I cannot explain this," they are marking the edge of the map. But IPTF-14 HLS is not alone. It is not the only star that has refused to follow the rules of stellar death. It is, in many ways, just the most spectacular example of a broader phenomenon that astronomers have been accumulating evidence for over the past several decades. And to understand the full scope of what is happening, you need to go back in time to the observations that first hinted at this weirdness, before anyone had the language to describe what they were seeing. Looking back through old photographic plates from the Palomar Observatory sky survey taken in 1954, astronomers found evidence of a brightening at the exact location of IPTF-14 HLS, 60 years before the supernova that was being observed in 2014. In 1954, 60 years earlier, something had exploded at that location 60 years before what everyone thought was the main event. The star had, it seemed, undergone a massive eruption in 1954 and somehow survived. And then it exploded again in 2014, and then it kept exploding over and over, brightening and dimming 5 times across nearly 2 years. The paper describing these findings, published in the journal Nature in 2017 by Yair Arkavi and colleagues, created an immediate sensation in the astrophysics community. The authors themselves called IPTF-14 HLS the most peculiar supernova ever observed. Not unusually energetic, not chemically strange, the most peculiar, the most confounding, the most resistant to explanation. And the question that hung in the air after that paper was published, the question that is still being debated today, is, what could possibly explain this? Here is where the theories begin. And it is important to be clear that what follows involves real scientific speculation, the kind of rigorous, evidence-based speculation that pushes physics toward its own frontier. These are not fringe ideas. They are serious proposals from serious scientists, and they demonstrate just how strange and poorly understood the deaths of massive stars still are, even after decades of observations and calculations. One of the leading theoretical explanations for objects like IPTF-14 HLS is a mechanism called pulsational pair instability. And to understand what pulsational pair instability is, you have to go even deeper into the physics of massive stars. The most massive stars in the universe, those with initial masses perhaps above 100 times the mass of our Sun, and sometimes several hundred times more massive, undergo a process in their cores that less massive stars never experience. At the extreme temperatures in the cores of these stellar giants, photons, particles of light, carry so much energy that they can spontaneously create pairs of electrons and their antimatter counterparts, positrons. This process, called pair production, actually reduces the radiation pressure in the core because the photons are being converted into matter instead of pushing outward. When the radiation pressure drops, gravity momentarily overcomes the outward force, and the core begins to collapse. But here is what makes this different from the final collapse of a normal massive star. In a pulsational pair instability event, the collapse does not go all the way. The compression heats the core so intensely that explosive nuclear burning begins. A sudden, violent burst of thermonuclear energy, and the energy released is enough to reverse the collapse. The star does not implode. Instead, it rebounds, and the rebound ejects an enormous shell of material into space. The star survives, for now. But the ejection does not stabilize the star permanently. It has lost mass, changed its internal structure, and the processes that led to pair instability are still operating. So the core can contract again, and the same thing can happen again. The star collapses, burns, rebounds, ejects material. And this can repeat, potentially many times, each explosion ejecting another shell of material into the space around the star. Each ejection is itself a massive explosion, what astronomers call a pulsational parinstability supernova, or PISN, event, but the star survives each one, until finally the star has either lost enough mass or undergone enough disruption that the final collapse happens. A true, terminal supernova that destroys the star completely. The visual result of this process, as seen from Earth, would be a source of light that brightens and dims repeatedly, with each pulsation corresponding to a new ejection event. If the ejected shells of material from earlier pulsations are still in the vicinity when a later pulsation occurs, the expanding material from the new explosion slams into the old shell, producing an additional burst of light as kinetic energy is converted to radiation. The bumps in the light curve of IPTF14 HLS could be explained by exactly this mechanism, each bump representing either a new pulsation or the interaction of expanding material with a previously ejected shell. But there is a problem. And the problem is the mass. Pulsational parinstability is predicted to occur in stars with initial masses above approximately 100 solar masses. These are the most massive stars in the universe. Rare, extreme objects that burn their fuel furiously and live short, spectacular lives. If IPTF14 HLS was a pulsational parinstability supernova, then the star that produced it would have needed to be extraordinarily massive. And when astronomers tried to model the progenitor star of IPTF14 HLS using all the available observational data, they found that while pulsational parinstability could explain some features of the event, it could not fully account for all of them. The light curve had the right shape in some ways, but the wrong timescales in others. The velocities of the ejected material were higher than some models predicted. The total energy of the event seemed, in some estimates, too large even for a parinstability event, which means either the models are incomplete, which they almost certainly are, because stellar physics at these extremes is genuinely at the frontier of what can be calculated, or something else entirely is going on. And this is the extraordinary thing about IPTF14 HLS and objects like it. They are not just strange observations. They are diagnostics of our own ignorance, windows into the gaps in our understanding of one of the most fundamental processes in the universe. Every time an astronomer stares at the light curve of IPTF14 HLS and says, "I cannot explain this," they are marking the edge of the map. But IPTF14 HLS is not alone. It is not the only star that has refused to follow the rules of stellar death. It is, in many ways, just the most spectacular example of a broader phenomenon that astronomers have been accumulating evidence for over the past several decades. And to understand the full scope of what is happening, you need to go back in time to the observations that first hinted at this weirdness, before anyone had the language to describe what they were seeing. Now, according to stellar physics, a supernova of the type that produced 1987A should have left behind a neutron star at its center. The prediction was unambiguous. The physics demanded it. But for more than 3 decades after the explosion, no neutron star was detected. Astronomers looked and looked, and the supernova remnant was bright and complex, and the suspected location of the neutron star was buried under all that expanding material, and direct detection proved frustratingly elusive. Some researchers began to speculate that perhaps the neutron star had further collapsed into a black hole, which would explain the lack of detection. A black hole radiates far less detectable energy than a neutron star in the early stages after formation. Then, in 2019, an extraordinarily careful analysis of data from the Atacama Large Millimeter Array, known as ALMA, combined with observations from the Hubble Space Telescope and the Chandra X-ray Observatory, produced tantalizing evidence of a blob of dust at the center of the supernova remnant that seemed to be warmer than its surroundings. The energy powering this warm region was consistent with what would be expected from a young neutron star, a pulsar, heating the material around it. The paper, published in 2019 by Phil Sagan and colleagues, was cautious but significant. It was the strongest evidence to date that a neutron star did indeed form in 1987A and is still radiating inside the remnant. And then in 2024, even more compelling evidence emerged. Observations with the James Webb Space Telescope and the Chandra Observatory, published in Science by Claes Fransson and a large international team, detected what appears to be a luminous central source within the 1987 A remnant consistent with X-ray and infrared emission from a neutron star or pulsar wind nebula. The evidence was described by many researchers as the strongest yet that the neutron star is there, hiding inside that cloud of dust and gas, still spinning, still radiating, a tiny dense relic of the original star's iron core, surviving at the heart of the explosion that obliterated everything around it. If confirmed, it would be the youngest directly detected neutron star from a supernova of known date, a remarkable achievement. But this raises a question so deep and so beautiful that you should really stop and sit with it for a moment. Sit with it right now, wherever you are. A star died. It died in an explosion of incomprehensible violence. Its outer layers were blasted into space. The iron core collapsed to a neutron star in fractions of a second. And 37 years later, as of 2024, that neutron star is still there, still hot, still spinning, still radiating energy into the cloud of its own disintegrated body. The star, in a very real sense, lives on. Not as what it was, not as the blue supergiant that hung in the sky of the large Magellanic Cloud for millions of years, but as something transformed, compressed, altered beyond recognition, and yet still emitting energy, still refusing to be silent. Is that not a kind of zombie? Not in the horror movie sense, but in the deeper, stranger sense, something that was destroyed and yet persists. Something whose death was real and total for 99% of what it was, and yet at the center of all that destruction, something survives, changed and alien, radiating into the dark. Now let us go further out. Let us talk about the objects that push this concept to its most extreme expression. Let us talk about superluminous supernovas, because these are events that take everything we have discussed about normal supernovas and multiply it by factors that strain comprehension. A normal core collapse supernova releases about 10 to the 44 joules of energy total, of which roughly 1% emerges as light. That 1%, about 10 to the 43 joules of light, is already enough to outshine entire galaxies for weeks. A superluminous supernova releases 10 to 100 times more light than that. Some of them are so bright they outshine their host galaxies by a factor of 100. These events are sometimes called ASLEEP, and they were only identified as a distinct class of objects in the mid-2000s. The discovery of superluminous supernovas was itself a story of data defying expectations. As robotic sky surveys became capable of monitoring millions of galaxies simultaneously, they began picking up transient events, objects that appeared suddenly and then faded, that were simply too bright to fit the known categories of supernovas. Astronomers at first questioned their instruments. They questioned their distance estimates. They questioned whether what they were seeing was some kind of observational artifact. But the evidence kept accumulating, and by around 2009, papers began to appear in the literature acknowledging that there was a new class of stellar explosion that simply did not fit the existing models. Something was pumping enormous amounts of extra energy into these events. But where was this extra energy coming from? This is the central mystery of superluminous supernovas, and it has generated several competing theories that are still being actively debated. One theory involves what is called a magnetar, a neutron star with an extraordinarily powerful magnetic field, perhaps 1,000 trillion times stronger than the Earth's magnetic field. When a neutron star forms in a supernova explosion, it typically spins very fast. Conservation of angular momentum, the same principle that causes a spinning figure skater to spin faster when they pull their arms in, causes the collapsing core to spin up dramatically as it contracts. A newly formed neutron star might complete several revolutions per second. If this neutron star has an extremely strong magnetic field, if it is a magnetar, then as it spins, it acts like a cosmic dynamo, radiating energy in the form of electromagnetic waves and particle winds. This spin-down energy can be enormous, and if it is deposited into the expanding supernova ejecta over a period of weeks to months, it would add an enormous extra source of luminosity. The supernova would shine brighter and longer than it otherwise would. The magnetar engine model, as it is called, was proposed independently by several groups of researchers in the late 2000s and early 2010s, and it has become one of the leading explanations for many superluminous supernovas. The mathematics works out in many cases. A neutron star with a millisecond spin period, meaning it completes a full rotation in about 1 millisecond, and a sufficiently strong magnetic field would shed its rotational energy on a timescale of weeks to months, which matches the observed light curves of many SLSNA. It is an elegant explanation, and in science, elegance is not proof, but it is encouraging. But here is the twist that brings us back to the zombie star concept in its most visceral form. In this model, the neutron star at the center of a superluminous supernova is not a passive relic. It is an active engine. It is continuously pumping energy into the surrounding ejecta, inflating a bubble of relativistic particles and magnetic fields inside the expanding shell of material, heating the gas from the inside, driving the ongoing luminosity. The supernova is not fading as it should because there is something at its center that will not let it fade. Something is keeping it alive. The star is dead, completely destroyed, and yet at its core, a tiny, impossibly dense remnant is spinning and radiating and refusing to let the light go out. If you take a step back and look at this from a certain angle, it is one of the most haunting images in all of science. Imagine the explosion happening. The outer layers of the star, layers that contain the hydrogen and helium and carbon and oxygen that the star fused over millions of years, are shredded and blasted outward at thousands of kilometers per second. The iron core collapses in a fraction of a second to a ball of neutrons 20 kilometers across. The collapse releases so much energy that the surrounding ejecta lights up with a brilliance 100 times greater than a normal supernova. And at the center of this brilliance, the neutron star is spinning. It is spinning perhaps 500 times per second, maybe 1,000 times per second, and its magnetic field is so strong that the electromagnetic energy streaming from it is measurable across billions of light years of space. The outer envelope of the star is gone. The star as a star is gone. But this small, ferociously energetic remnant is keeping the whole system lit. It is, in the most direct physical sense, refusing to let the death be complete. Ask yourself this. Could there be a mechanism by which a magnetar's energy output could be so sustained, so continuous, that it effectively prevents the supernova remnant from ever fully dimming? What would that look like over time scales of centuries or millennia? Would distant civilizations, if they observe such an event, even recognize it as a supernova at all, or would they see it as something else entirely? A persistent, anomalous source of light that defied all classification. We do not fully know the answers to these questions, and that uncertainty is itself meaningful, because it tells us something about the limits of our observational reach. Superluminous supernovas have only been systematically observed for about 15 years. The oldest known examples in our photographic records go back only a few decades. The long-term behavior of these objects, what happens to a superluminous supernova remnant over hundreds or thousands of years, is largely unknown. We have some theoretical predictions, but we have not been able to observe the late-time evolution of these events directly, because we have not been watching the relevant objects for long enough. In cosmic terms, our entire civilization has been observing the sky in any systematic way for an eye blink. The universe has been producing supernovas for over 13 billion years, and we have been paying careful attention for less than a century. There is another class of object that belongs in this story, and it is one of the most recently recognized and perhaps most extreme examples of stellar death gone wrong. These are called fast blue optical transients, or FBOTs, and they are so new as a recognized class of event that the literature on them is still being actively written. The first well-studied example, detected in 2018 and designated a 2018 cow, immediately nicknamed the cow by astronomers, because that is what the last 3 letters of the designation spell, and because scientists, for all their seriousness, are not immune to a good nickname, was, to put it simply, unlike anything anyone had seen before. A 2018 cow was located in a galaxy about 200 million light-years away, which is far enough that individually identifying the source required good telescope resolution, but close enough by extragalactic standards to get detailed observations. When it appeared, it brightened to peak luminosity in just 2 days. 2 days. Most supernovas take 1 to 2 weeks to reach peak brightness. The cow hit its maximum brightness in 48 hours. And it was extremely blue, hence the fast blue optical transient designation, indicating that the radiating surface was extremely hot, hotter than typical supernovas. At peak, it was radiating about 10 times more energy per second than a typical core collapse supernova. And then it faded, but not the way supernovas fade. It faded quickly in optical light but persisted in X-rays, and the X-ray emission showed a pattern of rapid fluctuations on timescales of milliseconds, which implied a compact central engine, either a neutron star or a black hole, that was actively accreting material and radiating at an extremely high rate. The paper presenting these findings, involving observing teams from dozens of institutions around the world using instruments ranging from radio telescopes to X-ray space observatories, described the cow as potentially representing a new class of stellar explosion whose mechanism was fundamentally different from known types. Some researchers proposed that the cow was caused by a massive star collapsing directly to a black hole while still embedded in dense circumstellar material the star had ejected before the collapse. In this scenario, the black hole begins accreting material from its immediate environment, driving jets or winds that slam into the surrounding shell, producing the rapid rise and extreme luminosity. Others proposed that it was a neutron star formed with extreme properties, a magnetar born spinning incredibly fast, that was dumping enormous amounts of energy into the surrounding gas. What is most remarkable about the cow and the growing family of FBOT events identified since, including objects like CSS 161010 at 2020 XND and others, is that they represent an entirely new manifestation of stellar death, one that was not even recognized as a category until a few years ago. They are not quite supernovas in the traditional sense. They are not quite gamma-ray bursts. They are something in between, or something adjacent, something whose physics is driven by a central engine that is actively participating in the explosion rather than just sitting quietly at the center. They are, in a profound sense, the most energetically active examples of the zombie phenomenon. The death of the star is powering something new, and that something new is keeping the light burning. Think about what this means. Think about the implications of discovering that stellar death is not a single, uniform process, but a rich, varied, complex phenomenon with multiple pathways, multiple outcomes, multiple degrees of violence and luminosity and duration. It means that when we look at the sky and see a point of light suddenly appear where no light was before, we do not yet know, in many cases, what we are looking at. We do not know if it is a simple death or a complicated one, a quiet end or a prolonged refusal. We do not know if it will be gone in weeks or persist for years. We do not know if the remnant at its center will be a quiet, cooling neutron star or a ferociously spinning magnetar that keeps the whole system lit for decades. This uncertainty is not a failure of science. It is a sign of a science that is genuinely confronting the complexity of its subject. The universe does not make things simple. The universe does not follow the textbook. And zombie stars, supernovas that refuse to die, stars that erupt and survive and erupt again, remnants that keep burning long after they should have gone dark, are one of the most vivid demonstrations of just how far beyond the textbook the universe is willing to go. Let us now take a step back from the individual events and look at the bigger picture, because the existence of zombie stars and superluminous supernovas and pulsational parent stability events and fast blue optical transients has implications that extend far beyond the immediate question of how individual stars die. These events matter for the universe as a whole. They matter for the chemistry of galaxies. They matter for the formation of planets, the evolution of life, and ultimately for questions about why the universe is the way it is. Start with chemistry. Every atom of iron in your blood was created in the core of a massive star that later exploded in a supernova. Every atom of calcium in your bones. Every atom of oxygen in the air you are breathing right now. These elements did not exist when the universe began. The universe began with hydrogen and helium and trace amounts of lithium. Everything else, every element heavier than those, every element that makes up the solid rocky planets, every element that makes up your body, was synthesized inside stars and scattered into space by stellar explosions. We are, in the most literal and non-metaphorical sense, made of stardust, of supernova remnants, of the material ejected by dying stars, and zombie stars, stars that undergo multiple eruptions, that eject huge amounts of material before their final explosion, may be disproportionately important contributors to this cosmic enrichment. A star that undergoes pulsational parinstability supernovas over the course of years or decades is ejecting material over and over again, seeding its surrounding environment with heavy elements long before the final explosion. The multiple ejected shells interact, mix, and disperse into the interstellar medium, the thin gas and dust that fills the space between stars. And when that material eventually collapses under gravity to form new stars and new planetary systems, it carries with it the chemical legacy of those repeated explosions. Some researchers have speculated, and it is important to emphasize this is speculative, that the first generation of stars in the universe, known as population 3 stars, may have been so massive that many of them underwent pulsational parinstability events before ultimately dying in complete parinstability supernovas. These hypothetical first stars formed from pure hydrogen and helium, without any of the heavier elements that act as coolants in star-forming regions, and this lack of metallicity, as astronomers call the presence of elements heavier than helium, may have allowed them to grow to masses of hundreds or even thousands of solar masses. If these enormous first stars then underwent parinstability events, they would have been among the most violent and prolific sources of heavy element enrichment in the early universe, seeding the raw material from which subsequent generations of stars and eventually planets would form. We have not yet directly observed a population 3 star. They formed in the first few 100 million years after the Big Bang, and they lived and died quickly. The James Webb Space Telescope, which launched in December 2021 and began science operations in 2022, is our most powerful tool for looking back to that early epoch, and astronomers are actively searching for signals that could indicate population 3 stellar populations or their supernova remnants. Some tentative evidence has been reported, spectral features in very distant galaxies that could be consistent with parinstability supernova enrichment, but no confirmed direct detection has been made yet. This is an area of active, exciting frontier research, and it is possible that within the next decade, JWST will provide the first direct evidence of the most massive and most ancient stars in the universe having died in exactly the kind of repeated, zombie-like explosions we've been describing. Now here is a thought that should genuinely give you pause. We have been talking about supernovas as events that happen elsewhere, in distant galaxies, in the Large Magellanic Cloud, in star-forming regions far from our solar system. But our galaxy, the Milky Way, has about 100,000 massive stars, and massive stars die in supernovas at a rate estimated at roughly 1 or 2 per century in a galaxy like ours. The last confirmed supernova in our galaxy that was visible to the naked eye was the one observed by Johannes Kepler in 1604, Kepler's star, located about 20,000 light-years from Earth, which shone brightly in the night sky for over a year and was extensively studied by astronomers in Europe and Asia. Before that, Tycho Brahe's supernova of 1572. And before that, the one that created the Crab Nebula in 1054, which was recorded by Chinese and other astronomers as a star so bright it was visible in daylight for 23 days. The fact that we have not seen a galactic supernova since 1604, 4 centuries, is not evidence that they have not occurred. It is almost certainly evidence that any supernovas occurring in our galaxy in the past 4 centuries have been obscured by the dense clouds of gas and dust that fill the galactic plane, making them invisible to optical telescopes from Earth's position. Cassiopeia A, a supernova remnant in the constellation Cassiopeia, is thought to have been created by a stellar explosion around 1680, just 76 years after Kepler's star, and yet no record of it being observed by any contemporary astronomer has been convincingly identified. It was simply hidden behind dust. We found it later by its radio emission. It is a ghost of an explosion that nobody saw. And it is worth asking, and please ask yourself this right now, whether there could be a zombie star event happening right now, somewhere in our galaxy, hidden behind clouds of dust, that no human being has ever seen or ever will see with an optical telescope. An event like IPTF-14 HLS, happening inside the Milky Way, cycling through its repeated eruptions in perfect invisibility, pouring out energy into a region of the galaxy we cannot observe. The radio waves and X-rays and infrared radiation from such an event might already be reaching us, already passing through our instruments, already recorded in datasets waiting to be analyzed. Astronomers using the Very Large Array, the Chandra X-ray Observatory, the Spitzer Space Telescope, the James Webb Space Telescope, are constantly surveying the galaxy at wavelengths that penetrate the dust, and they find remarkable things. Whether they have found a hidden zombie star eruption, or will find one, is an open question. Let us now enter the territory of the truly extreme, because there is a version of the zombie star concept that goes beyond even what we have discussed so far. There is a type of supernova, extremely rare, perhaps unique in the observable universe to a handful of known examples, that represents not just a star refusing to die, but a star whose death produces something so bizarre, so contrary to expectation, that it forced astrophysicists to revise fundamental assumptions about what is possible in nature. This is the type IAX supernova, sometimes nicknamed the zombie star supernova, and the story behind it is one of the strangest in all of stellar astronomy. To understand type IAX supernovas, you first need to understand the more familiar type Ia supernova. A type Ia supernova is produced not by the core collapse of a massive star but by a white dwarf, the stellar remnant left behind by a sun-like star after its outer layers drift away as a planetary nebula. White dwarfs are small, dense, hot objects, and in isolation they simply cool down over billions of years. But white dwarfs are not always in isolation. Many stars exist in binary systems, two stars orbiting each other. And when one of those stars evolves and dies, leaving behind a white dwarf, and its companion star later expands into a red giant, the white dwarf can begin to accrete material from the companion. Mass flows from the companion star onto the white dwarf surface, slowly building up until the total mass of the white dwarf approaches the Chandrasekhar limit, 1.4 solar masses. At that point, carbon fusion ignites throughout the white dwarf in a thermonuclear runaway reaction, and the resulting explosion, a type Ia supernova, completely destroys the white dwarf. Every atom of it. No remnant. No neutron star. Just expanding gas. Type Ia supernovas are enormously important in cosmology because they have a relatively consistent peak luminosity. They are what astronomers call standard candles, objects of known intrinsic brightness that allow you to calculate their distance from how bright they appear. By measuring the distances and recession velocities of type Ia supernovas in distant galaxies, astronomers in the late 1990s discovered that the expansion of the universe is accelerating. A finding so extraordinary that it earned the 2011 Nobel Prize in Physics. The accelerating expansion is attributed to dark energy, a mysterious component of the universe whose nature is one of the deepest unsolved problems in all of physics. So type Ia supernovas have been absolutely central to our understanding of the cosmos. But it turns out that not all thermonuclear supernovas in white dwarfs go to completion. Some of them, the type IAX events, appear to represent a partial detonation. The thermonuclear runaway begins, spreads through the white dwarf, releases an enormous amount of energy, but does not fully disrupt the star. Instead of exploding completely, the white dwarf ejects a fraction of its mass and then settles back down into a surviving remnant, a zombie star in the most direct sense that astronomers have applied that term. The surviving remnant is thought to be a highly unusual object, a stellar core that has been partially burned, enriched with radioactive nickel-56 and other heavy elements from the thermonuclear burning, spinning fast, and radiating with a bizarre spectrum that does not match anything else known. The theoretical prediction of this surviving remnant was made by researchers at the Harvard-Smithsonian Center for Astrophysics, including Saurabh Jha and colleagues, based on detailed modeling of the type IAX explosion mechanism. In 2014, a paper was published that described the observational characteristics of the predicted zombie white dwarf. It should be luminous, but with an unusual spectrum showing elements inconsistent with a normal white dwarf or a normal star. It should be located at the center of a supernova remnant or near the position of a historical type IAX event. And it should be moving through space in a way consistent with having received a kick from the explosion. No confirmed example of this zombie white dwarf remnant had been directly observed as of the time of that paper. The prediction was theoretical. But there is a supernova remnant in our galaxy, designated SN 1000XS remnant, and more specifically a peculiar object in the remnant of a historical event, that some researchers have tentatively associated with the kind of surviving remnant that the zombie white dwarf model predicts. And there are other candidates in nearby galaxies. The search for a confirmed zombie white dwarf, the surviving core of a partially detonated thermonuclear supernova, is an active area of observational astronomy. It is the search for the physical embodiment of a star that exploded and survived. Think about how paradoxical that is. A star that exploded and survived. Not metaphorically, not in the sense that some remnant forms afterward, but in the sense that the object that exploded still exists, damaged and changed and enriched by its own partial destruction, continuing to radiate while the material it expelled expands around it. It experienced a supernova. It was a supernova, and it is still there. What does it feel like to contemplate that? Put yourself in the position of that object, not as a human consciousness in the body of a star, but just as a thought experiment. Something inside you ignites. The thermonuclear fire spreads through your core. The explosion is real and massive and violent. Material tears away from you. And then, somehow, despite all of that, you are still coherent, still structured, still a thing, rather than just a cloud of expanding debris. You have been partly destroyed and partly survived your own destruction. What kind of physics allows for that? What extraordinary fine-tuning of the conditions? The total mass, the composition, the geometry of the explosion produces an outcome so precisely between total annihilation and mere disruption. This is one of the questions that zombie stars force astrophysicists to confront. How sensitive are the outcomes of stellar death to the initial conditions? We know that a small difference in initial mass can determine whether a star collapses to a neutron star or a black hole. We know that the metallicity of the star, its chemical composition, affects how it evolves and how it dies. We know that rotation rates, magnetic field strengths, binary companion properties, and dozens of other factors all influence the final moments. But the sensitivity of the outcome to these factors in the most extreme cases, the cases that produce zombie stars, superluminous supernovas, bots, pulsational parent stability events, is still being worked out. We are, in many ways, still at the beginning of understanding the full parameter space of stellar death. And here is a thought that is purely speculative, but worth exploring, because it touches on something profound about the relationship between physics and possibility. If the conditions that produce zombie stars are rare but not vanishingly rare, if something like 1 in 1,000 supernovas or 1 in 10,000 produces an event like IPTF14 HLS or the Cow, then given that the observable universe contains roughly 2 trillion galaxies, each containing perhaps hundreds of billions of stars, and given that massive stars have been exploding since a few 100 million years after the Big Bang, the total number of zombie star events that have occurred in the history of the universe could be astronomical. Literally astronomical. There could have been billions of these events, spread across cosmic time and space, each one producing a prolonged, luminous display that no human eye has ever seen because the light from it arrived before we existed, or is arriving now but from a direction we have not yet looked, or will arrive long after our civilization is gone. The universe is enormous. It is old, and it has been doing violent, extraordinary things in its distant regions for billions of years, mostly without any witness. We are, in this regard, like someone who moves into a house and discovers that the walls are full of the most extraordinary graffiti from centuries of occupants, graffiti left in paint that glows in certain wavelengths of light, and we're just beginning to develop the instruments that can see those wavelengths. Every new telescope, every new survey, every new detection technique is another lantern held up to another part of the wall, revealing another layer of what has been happening in this universe for a very long time. Let us talk now about what might be the most emotionally resonant aspect of this entire story, and that is the way in which these extreme stellar events connect directly to the conditions for life. Because this is not just an abstract astronomical story. This is ultimately a story about why we exist, and what kinds of cosmic violence were necessary to create the conditions under which we became possible. The elements needed for life, carbon, nitrogen, oxygen, phosphorus, sulfur, iron, and many trace elements, were all created inside stars. The process of stellar nucleosynthesis, the forging of heavy elements in stellar cores and supernova explosions, is the mechanism by which the universe gradually enriched itself with the building blocks of chemistry and ultimately biology. A universe that had no supernovas, a universe in which stars simply fused hydrogen and then quietly faded, would be a universe that stayed hydrogen and helium forever. No rocky planets, no carbon-based chemistry, no life. The violence of stellar death is not incidental to our existence. It is fundamental to it. We are here because stars died catastrophically and scattered their contents across the galaxy. And zombie stars, stars that die multiple times, stars that eject material again and again before their final explosion, may be even more potent contributors to this enrichment process than ordinary supernovas. A pulsational pair instability event, by definition, involves multiple ejections of material, each one spreading heavy elements into the surrounding interstellar medium. The interaction between those ejected shells can produce additional nucleosynthesis, additional element creation, as the shocks heat and compress the material in ways that go beyond what happens in a single explosion. Some researchers have proposed that certain isotopic anomalies found in meteorites in our own solar system, small deviations from the expected ratios of certain isotopes, could be signatures of a nearby pulsational pair instability event that enriched the molecular cloud from which the Sun and planets formed about 4.6 billion years ago. This is speculative, and the evidence is not conclusive, but the idea that a zombie star explosion might have directly influenced the chemical composition of our own solar system is both extraordinary and scientifically plausible. Consider what that would mean if it were true. It would mean that a star billions of years before the Sun existed exploded not once but multiple times, spewing its guts into the surrounding gas cloud, and that some of that material eventually found its way into the nebula from which our solar system condensed. Some of the atoms in your body, atoms of carbon, nitrogen, oxygen, may have passed through the core of a zombie star. They may have been forged in the thermonuclear hell of a pulsational pair instability explosion, scattered into space, drifted through the interstellar medium for millions of years, been incorporated into a molecular cloud, and then ultimately found their way into the rocky material of the early Earth. And from there through the long chain of chemical evolution that eventually produced proteins and DNA in cells and organisms, and eventually you, sitting wherever you are right now, listening to this story. That is not poetic license. That is a literal description of what physical processes, traced backward, would imply if the hypothesis of zombie star enrichment of our solar system's birth cloud is correct. We are made of the debris of stars that refuse to die quietly. Now, let us take a different angle on this story, because there is a dimension to the zombie star phenomenon that we have not yet fully explored, and it involves the nature of time and observation. When we see a supernova, even one that brightens and dims repeatedly over months or years, we are seeing an event that happened years ago, or decades ago, or millions or billions of years ago. The light we observe is not the present state of the object. It is the past state, communicated to us at the speed of light across the intervening distance. When astronomers observed IPTF 14 HLS brightening and dimming for 600 days in 2014 and 2015, the actual explosions they were watching had occurred roughly 500 million years ago, when the light began its journey toward Earth. 500 million years ago. The zombie star of IPTF 14 HLS was alive and exploding during the Cambrian explosion of life on Earth, the period when most of the major animal phyla first appeared in the fossil record. While trilobites were crawling across the floors of ancient oceans, while the first fish were evolving in Cambrian seas, while complex multicellular life was just beginning to diversify and fill the ecological niches of a young biosphere. At that very same time, in a galaxy 500 million light-years away, a star was dying and refusing to die, exploding repeatedly, lighting up the surrounding space with a brilliance that we would only see 500 million years later. The timescales involved in astronomy have this quality of making everything human feel simultaneously important and infinitesimally small. And here's a question to ask yourself. If there are civilizations in that galaxy, civilizations that were around 500 million years ago when IPTF 14 HLS actually exploded, what did they see? If they were close enough, a few thousand light years from the explosion, did it affect their sky? Did it affect their planet? Did it trigger any kind of response, scientific or cultural or existential? We will never know. The light of any civilization in that galaxy, if one exists and if it is pointing communication our way, would be in transit and would not arrive for hundreds of millions of years. We are separated from the moment of that event not just by space but by a gulf of time so large that everything we know about human history is less than a rounding error within it. This is one of the reasons that zombie stars and superluminous supernovas are particularly valuable to cosmologists. Because they are so much brighter than ordinary supernovas, they can be seen at much greater distances. Greater distances meaning further back in time. A superluminous supernova occurring in a galaxy at redshift 2, meaning we are seeing it as it was when the universe was roughly 3.3 billion years old, can be detected with current technology. An ordinary supernova at the same distance would be far too faint. So the extreme brightness of superluminous supernovas allows astronomers to probe the star formation history of the early universe, to test models of how galaxies evolved, and potentially to use these events as a new kind of distance indicator, a new type of standard candle, to map the expansion of the universe at epochs when type Ia supernovas are too faint to observe. Some researchers are actively working on calibrating superluminous supernovas as distance indicators, and if they can be standardized, if the systematic variations in their peak luminosities can be understood well enough to correct for them, they could extend our cosmic distance ladder to redshifts far beyond what type Ia supernovas can reach, potentially providing new constraints on the nature of dark energy and the geometry of the universe. This is not just speculative. It is an active research program, pursued by teams at institutions around the world, using data from surveys like the Zwicky Transient Facility, the Dark Energy Survey, and soon the Vera C. Rubin Observatory's Legacy Survey of Space and Time. Let us now talk about what the Vera C. Rubin Observatory is going to mean for this field, because it represents a step change in our ability to find and study transient events like superluminous supernovas and spots and pulsational pair instability events. The Rubin Observatory, currently under construction in Chile and expected to begin its primary survey in 2025, will repeatedly image the entire southern sky every few nights with a camera so large, 3,200 megapixels, that a single image covers an area 40 times larger than the full moon. Every time it images the sky, it will compare the new images to previous images and flag any source that has changed. A star that has brightened, even slightly, will be detected within days. The stream of alerts this telescope will produce is expected to number in the millions per night. Every night. The scale of the data it will produce is entirely without precedent in the history of astronomy. For zombie stars and related phenomena, this means that events like IPTF 14 HLS, which showed its unusual behavior over a period of many months, will be caught early and monitored in exquisite detail. Events like the cow, which rose to peak brightness in 2 days, will be detected within hours of their start, giving observers around the world the chance to point other telescopes at the event immediately, before the most rapidly evolving features have faded. The FBOT population, which is currently known from only a handful of well-studied examples, will explode, so to speak, into the hundreds or thousands, providing the statistical sample needed to understand what these events are, how they form, and what range of properties they have. The pulsational pair instability supernova population, currently known from perhaps a handful of convincing candidates, will be dramatically enlarged. And crucially, the Rubin Observatory will have the sensitivity and the cadence to detect the kind of pre-supernova brightening events that represent stars undergoing pre-explosion eruptions. Stars like what Eta Carinae was in the 1840s, or what the progenitor of IPTF 14 HLS apparently was in 1954, stars in the final years of their lives, undergoing massive eruptions before the main event, are exactly the kind of sources that will appear in the Rubin alert stream. Identifying these objects before they explode would allow astronomers to point other instruments at them immediately, studying the pre-explosion behavior in real time and ultimately observing the main explosion from the very beginning, with full multi-wavelength coverage. This is the dream, catching a zombie star in the act of being born, from the very first moment. The theoretical community working on zombie stars is also in the midst of a revolution driven by computational power. Simulating a supernova, modeling the collapse of a stellar core, the propagation of the shock wave, the development of the explosion, the subsequent evolution of the remnant, is one of the most computationally demanding problems in all of astrophysics. For decades, three-dimensional simulations of core-collapse supernovas were beyond reach, and researchers had to work with simplified one-dimensional models that could not capture the complex fluid dynamics, convection, neutrino transport, magnetic field effects, and rotation that all play important roles in real explosions. The results of one-dimensional models were often wildly inconsistent with observations. Simulated supernovas frequently refused to explode at all. The shock stalled, and nothing happened. This was known as the supernova problem, and it was a serious embarrassment for the field. Three-dimensional simulations, enabled by the growing power of supercomputers at national laboratories and research universities, have made enormous progress in the past decade. Groups at institutions like Oak Ridge National Laboratory, the Max Planck Institute for Astrophysics, the California Institute of Technology, and Princeton University have developed increasingly realistic 3D codes that can simulate the first few seconds after core collapse with enough detail to actually produce explosions. These simulations have shown that turbulence, the chaotic, three-dimensional mixing of hot and cold gas inside the shock material, plays a crucial role in helping the shock wave revive and propagate outward. Without turbulence, many simulated supernovas stall. With turbulence included, they explode. This was a triumph of theory meeting computation. But zombie star events, pulsational parent stability supernovas, magnetar-powered superluminous supernovas, BOTS, are even harder to simulate than ordinary core-collapse supernovas, because they involve longer timescales, more complex progenitor structures, and in some cases entirely different physical mechanisms. Simulating a pulsational parent stability sequence, the initial collapse, the explosive bounce, the ejection of material, the settling, the next pulse, requires tracking the evolution of an extremely massive star over years of real time, which corresponds to tens of thousands of computational time steps with complex physics at each step. These simulations are being done at places like the University of California, Santa Cruz and the University of Minnesota, but they require enormous computational resources and make simplifications that may not fully capture the real physics. The comparison between these simulations and the observations of events like IPTF-14 HLS is an ongoing dialogue, with each new observation revealing new features that the simulations need to reproduce. Ask yourself this question and sit with it for a moment. What would it mean for our understanding of the universe if we could fully simulate a zombie star event from beginning to end with perfect fidelity, and then compare that simulation to observation and find perfect agreement? What would that tell us? It would tell us that we truly understand the physics of the most violent events in the universe. That we have found the mathematical language that correctly describes matter and energy in conditions that exceed anything achievable in any laboratory on Earth. That the equations of general relativity, nuclear physics, particle physics, and fluid dynamics combined are complete enough to describe the death and the prolonged refusal to die of a star. That is an extraordinary thing to aspire to. And we are not there yet, but we are moving toward it. The gap between our current understanding and that aspiration is where the most exciting science lives. And that gap is not empty. It is full of surprising observations, competing theories, spirited debates, and genuine mystery. It is the most intellectually alive place in astrophysics right now. One of the deepest mysteries in this field involves what happens to the magnetic field of a newly formed neutron star, because the magnetic field is central to the magnetar engine model that explains many superluminous supernovas. We know that neutron stars can have magnetic fields orders of magnitude stronger than ordinary pulsars. The most strongly magnetized neutron stars, the magnetars proper, which are a distinct subclass of neutron star, have magnetic fields of 10 to the power of 15 Gauss. For comparison, the Earth's magnetic field is about 0.5 Gauss. A refrigerator magnet is a few hundred Gauss. The strongest sustained magnetic fields produced in any laboratory on Earth are a few tens of Tesla, which is a few 100,000 Gauss. A magnetar's field, at 10 to the 15 Gauss, is 10 billion times stronger than the most powerful magnets humans have ever created. The electromagnetic forces at the surface of a magnetar are so strong that they would tear atoms apart before you could get close to the object. Where does this field come from? How is it generated? The short answer is that we are not entirely sure. One leading theory, called the convective dynamo model, proposes that immediately after a neutron star forms, the extreme temperatures cause vigorous convective motions inside the star, hot material rising, cool material sinking, and these motions, combined with the rapid rotation of the neutron star, can amplify a seed magnetic field through a dynamo mechanism similar to, but vastly more powerful than, the one that generates the Earth's magnetic field. If the neutron star is born spinning very fast, and if convection is vigorous enough, the dynamo can amplify the magnetic field to magnetar strengths within seconds of the star's birth. But the conditions under which this happens are not well understood. Not every neutron star is a magnetar. In fact, magnetars are rare. Only a few dozen are known in our galaxy, compared to the larger population of ordinary pulsars. What determines whether a newly formed neutron star becomes a magnetar? Is it the rotation rate at birth? The structure of the progenitor star? The details of the convection pattern? These questions are deeply connected to the question of what produces superluminous supernovas, because if the magnetar engine model is correct, then the production of a superluminous supernova requires the birth of a magnetar, which requires specific conditions that are presumably rare. The rarity of superluminous supernovas. They are estimated to occur at roughly 0.1% the rate of ordinary core-collapse supernovas, or possibly somewhat more depending on the redshift and environment, is roughly consistent with the expected rarity of magnetar formation under the extreme conditions required. But roughly consistent is not the same as proven. The magnetar model for superluminous supernovas makes specific predictions about the time evolution of the light curve, the spectral properties, the polarization of the light, and the X-ray and radio emission. Some of these predictions match observations well. Others are more problematic. There are superluminous supernovas whose light curves show features, bumps, sudden drops, unusual late-time behavior, that pure magnetar models struggle to explain. Some researchers have proposed hybrid models involving both a magnetar engine and the interaction of ejecta with a dense circumstellar shell, a combination that can produce light curve features that neither mechanism alone can explain. The interaction model, the idea that additional luminosity comes from the supernova ejecta slamming into previously ejected material from the progenitor star, is worth dwelling on, because it is another form of the zombie star phenomenon. If a star ejects massive shells of material in the years or decades before its final explosion, and then the supernova ejecta sweeps into those shells, the resulting shock converts kinetic energy into radiation with a process called circumstellar material interaction, or CSM interaction. The more dense the circumstellar material and the faster the ejecta, the more luminous the interaction. In some cases, the interaction alone can account for the extra luminosity of a superluminous supernova without needing a magnetar engine at all. The distinction matters because it implies very different physical mechanisms and therefore different connections to stellar evolution theory. If superluminous supernovas are powered by magnetar engines, they are telling us about the birth of the most extreme neutron stars. If they are powered by CSM interaction, they are telling us about the most extreme pre-supernova mass loss events, events in which massive stars eject enormous amounts of material in the final years of their lives, perhaps through mechanisms like pulsational pair instability, and that material then becomes the fuel for the interaction luminosity. In the latter scenario, the superluminous supernova is not primarily a feature of the explosion mechanism but of the progenitor's life history, specifically of the extraordinary violence of its final years. And in both scenarios, the zombie star is present. In the magnetar scenario, the zombie is the neutron star, spinning at the center, refusing to let the light fade. In the CSM interaction scenario, the zombie is the progenitor itself, the star that spent its final years ejecting material, erupting, surviving its own eruptions, building up a cocoon of shells around itself, and then finally dying in an explosion that was amplified by all those prior ejections. The zombie is the eruption before the eruption, the prolonged death that preceded the final death. Is it possible that many superluminous supernovas involve both mechanisms simultaneously? Absolutely, and some theoretical models explicitly incorporate both. The magnetar provides an internal energy source that drives the ejecta to high velocities, increasing the luminosity of the CSM interaction. The CSM interaction provides an external source of radiation that adds to the magnetar-powered luminosity. The two mechanisms reinforce each other. In this combined picture, a superluminous supernova is not just one extraordinary thing happening. It is two extraordinary things happening at the same time, both connected to the same progenitor star's unusual history. The gap between our current understanding and that aspiration is where the most exciting science lives. And that gap is not empty. It is full of surprising observations, competing theories, spirited debates, and genuine mystery. It is the most intellectually alive place in astrophysics right now. One of the deepest mysteries in this field involves what happens to the magnetic field of a newly formed neutron star, because the magnetic field is central to the magnetar engine model that explains many superluminous supernovas. We know that neutron stars can have magnetic fields orders of magnitude stronger than ordinary pulsars. The most strongly magnetized neutron stars, the magnetars proper, which are a distinct subclass of neutron star, have magnetic fields of 10 to the power of 15 Gauss. For comparison, the Earth's magnetic field is about 0.5 Gauss. A refrigerator magnet is a few hundred Gauss. The strongest sustained magnetic fields produced in any laboratory on Earth are a few tens of Tesla, which is a few 100,000 Gauss. A magnetar's field, at 10 to the 15 Gauss, is 10 billion times stronger than the most powerful magnets humans have ever created. The electromagnetic forces at the surface of a magnetar are so strong that they would tear atoms apart before you could get close to the object. Where does this field come from? How is it generated? The short answer is that we are not entirely sure. One leading theory, called the convective dynamo model, proposes that immediately after a neutron star forms, the extreme temperatures cause vigorous convective motions inside the star, hot material rising, cool material sinking, and these motions, combined with the rapid rotation of the neutron star, can amplify a seed magnetic field through a dynamo mechanism similar to, but vastly more powerful than, the one that generates the Earth's magnetic field. If the neutron star is born spinning very fast, and if convection is vigorous enough, the dynamo can amplify the magnetic field to magnetar strengths within seconds of the star's birth. But the conditions under which this happens are not well understood. Not every neutron star is a magnetar. In fact, magnetars are rare. Only a few dozen are known in our galaxy, compared to the larger population of ordinary pulsars. What determines whether a newly formed neutron star becomes a magnetar? Is it the rotation rate at birth? The structure of the progenitor star? The details of the convection pattern? These questions are deeply connected to the question of what produces superluminous supernovas, because if the magnetar engine model is correct, then the production of a superluminous supernova requires the birth of a magnetar, which requires specific conditions that are presumably rare. The rarity of superluminous supernovas. They are estimated to occur at roughly 0.1% the rate of ordinary core-collapse supernovas, or possibly somewhat more depending on the redshift and environment, is roughly consistent with the expected rarity of magnetar formation under the extreme conditions required. But roughly consistent is not the same as proven. The magnetar model for superluminous supernovas makes specific predictions about the time evolution of the light curve, the spectral properties, the polarization of the light, and the X-ray and radio emission. Some of these predictions match observations well. Others are more problematic. There are superluminous supernovas whose light curves show features, bumps, sudden drops, unusual late-time behavior, that pure magnetar models struggle to explain. Some researchers have proposed hybrid models involving both a magnetar engine and the interaction of ejecta with a dense circumstellar shell, a combination that can produce light curve features that neither mechanism alone can explain. The interaction model, the idea that additional luminosity comes from the supernova ejecta slamming into previously ejected material from the progenitor star, is worth dwelling on, because it is another form of the zombie star phenomenon. If a star ejects massive shells of material in the years or decades before its final explosion, and then the supernova ejecta sweeps into those shells, the resulting shock converts kinetic energy into radiation with a process called circumstellar material interaction, or CSM interaction. The more dense the circumstellar material and the faster the ejecta, the more luminous the interaction. In some cases, the interaction alone can account for the extra luminosity of a superluminous supernova without needing a magnetar engine at all. The distinction matters because it implies very different physical mechanisms and therefore different connections to stellar evolution theory. If superluminous supernovas are powered by magnetar engines, they are telling us about the birth of the most extreme neutron stars. If they are powered by CSM interaction, they are telling us about the most extreme pre-supernova mass loss events. Events in which massive stars eject enormous amounts of material in the final years of their lives, perhaps through mechanisms like pulsational pair instability, and that material then becomes the fuel for the interaction luminosity. In the latter scenario, the superluminous supernova is not primarily a feature of the explosion mechanism but of the progenitor's life history, specifically of the extraordinary violence of its final years. And in both scenarios, the zombie star is present. In the magnetar scenario, the zombie is the neutron star, spinning at the center, refusing to let the light fade. In the CSM interaction scenario, the zombie is the progenitor itself, the star that spent its final years ejecting material, erupting, surviving its own eruptions, building up a cocoon of shells around itself, and then finally dying in an explosion that was amplified by all those prior ejections. The zombie is the eruption before the eruption, the prolonged death that preceded the final death. Is it possible that many superluminous supernovas involve both mechanisms simultaneously? Absolutely, and some theoretical models explicitly incorporate both. The magnetar provides an internal energy source that drives the ejecta to high velocities, increasing the luminosity of the CSM interaction. The CSM interaction provides an external source of radiation that adds to the magnetar-powered luminosity. The two mechanisms reinforce each other. In this combined picture, a superluminous supernova is not just one extraordinary thing happening. It is two extraordinary things happening at the same time, both connected to the same progenitor star's unusual history. Now here is something that should genuinely make you pause and think about your place in the universe. There are massive, rapidly rotating stars in our galaxy. Not many of them, but some that are oriented such that if they were to collapse to a rapidly spinning black hole and drive a relativistic jet, that jet might be pointed in our direction. Eta Carinae, which we discussed earlier, is one such candidate. The jet axis of Eta Carinae is inclined such that, based on current estimates, a gamma-ray burst jet would not be directed at Earth. But the uncertainty in that estimate is not zero. And there are other candidate stars. WR-104, a Wolf-Rayet binary star about 8,000 light-years away, was for a while considered a possible gamma-ray burst threat to Earth. The binary system appears to be oriented nearly face-on to us, which could mean a jet pointing in our direction. However, more recent analysis has suggested the situation is less alarming than initially feared, and the exact orientation is uncertain. But the point is not that any particular star is definitely going to irradiate us. The point is that the possibility exists, and that we live in a galaxy where the deaths of massive stars are not benign events happening safely far away. They are processes that could, under the right circumstances, have consequences on Earth. This is not science fiction. It is stellar physics. The fact that life has continued to evolve on Earth for over 3 billion years without being wiped out by a nearby gamma-ray burst is itself significant. It suggests either that such events in our galactic neighborhood have been rare over that timescale, which is plausible given that the most likely gamma-ray burst progenitors tend to be found in actively star-forming, low-metallicity environments, and our local galactic neighborhood has relatively high metallicity, or that we have simply been lucky, or both. Some researchers, though this is speculative, have considered the gamma-ray burst rate in the context of the galactic habitable zone concept. The idea that certain regions of the galaxy are more hospitable to complex life than others, partly because they are less frequently exposed to nearby violent stellar deaths. The outer parts of the galaxy may be too sparsely populated with stars for planetary systems to receive the heavy element enrichment needed for rocky planet formation. The inner parts of the galaxy are extremely active, with high rates of star formation and stellar death, and therefore higher rates of gamma-ray burst irradiation. The intermediate zones, like the one our solar system occupies, may offer the right balance. This is a fascinating and deeply speculative idea, but it connects the physics of zombie stars and gamma-ray bursts to the fundamental question of why we exist where we exist in the galaxy. We have been traveling through an enormous landscape of science, from the basic physics of stellar death to the most extreme and exotic events at the frontier of astrophysical observation. Let us now slow down and look at a specific, concrete example that brings many of these threads together. The case of SN 2006 JC. This was a supernova in a galaxy called UGC 4904, about 77 million light-years from Earth, and it holds the remarkable distinction of being the first case in which astronomers directly observed a major pre-supernova outburst from the progenitor star. In October 2004, 2 years before the main supernova, astronomers detected a brightening at the location of what would become SN 2006 JC. The brightening was significant. It represented an enormous eruption from the progenitor star, but it did not look like a supernova, and at the time it was catalogued and the location was subsequently lost track of amid the flood of other observations being processed. 2 years later, in October 2006, a full supernova exploded at exactly the same location. It was only then, going back through the archive data, that the 2004 outburst was recognized for what it was: a direct observation of the star undergoing a massive pre-supernova eruption exactly 2 years before its death. The star had erupted, survived, and then, 2 years later, died for real. What makes SN 2006 JC even more extraordinary is its spectral type. It was classified as a type Ibn supernova, a rare and unusual class of supernova characterized by helium-rich circumstellar material. The spectra showed strong interaction between the supernova ejecta and a dense shell of helium gas surrounding the star, a shell that was presumably ejected in the 2004 outburst. The interaction was producing additional luminosity on top of the explosion itself, making SN 2006 JC appear brighter and evolving differently than it would have without the surrounding shell. The zombie star's final pre-death eruption was literally shaping the appearance of its terminal explosion. The progenitor star of SN 2006 JC was a Wolf-Rayet star, a massive luminous star that has shed its outer hydrogen envelope through an extremely powerful stellar wind, exposing its helium core. Wolf-Rayet stars are among the most massive and most evolved stars known, and they are thought to be immediate precursors of core-collapse supernovas. The 2004 outburst from the SN 2006 JC progenitor was, at the time, without parallel in the observational record. No one had previously caught a Wolf-Rayet star undergoing a major eruption 2 years before its death. The significance of the discovery was immediately recognized, and a paper describing the observations, by Pastorello and colleagues, was published in Nature in 2007, alongside an independent paper on the discovery. The observation became one of the most cited and most influential in the recent history of supernova research because it demonstrated directly, not inferred from models, not predicted theoretically, but actually observed, that massive stars can undergo major eruptions in the final years of their lives. This finding has profound implications for how we think about the connection between pre-supernova mass loss and the eventual explosion. If the progenitor of SN 2006 JC erupted 2 years before its death, and if other massive stars do similar things, then the space around many supernovas at the time of explosion should be filled with recently ejected shells of material. The supernova ejecta would inevitably slam into these shells, producing CSM interaction that modifies the light curve, the spectra, and the total energy budget of the observed explosion. The supernova is not happening in a clean, empty environment. It is happening inside the remnants of the star's own recent history, inside the shells it ejected in its final paroxysms of activity. The supernova is, in a very physical sense, colliding with itself, with the material it threw off when it was still alive. And the more we observe, the more we find that this kind of circumstellar material is ubiquitous. A growing body of evidence suggests that many, Perhaps most core-collapse supernovas show some evidence of interaction with circumstellar material in their first hours to days of light curve evolution. This evidence comes from very early observations taken within the first day of a supernova's detection, that show a brief flash of blue light above what the underlying explosion would produce. This shock cooling emission and associated features are signatures of the supernova shock wave hitting material that the star ejected in its final days to years. The prevalence of this early emission suggests that pre-explosion mass loss is not rare and exotic but common and potentially universal for massive stars. What this means is that every massive star that explodes as a supernova may be, to some degree, a zombie star. A star that experienced eruptions, ejections, or at least enhanced mass loss in its final years, and whose death is therefore shaped by the mess it made while it was still alive. The zombie character of these events is not confined to the exotic extremes like IPTF-14 HLS. It may be a fundamental feature of how massive stars die. The question is one of degree. Some stars eject a little material and the interaction is brief and faint. Others eject enormous amounts of material, and the interaction dominates the light curve for weeks or years. And in the most extreme cases, the pulsational pair instability supernovas, the ejection happens in massive repeated pulses over years or decades, and the star may have scattered enormous shells of material across light years of surrounding space before finally dying. This emerging picture is one of the most exciting developments in modern astrophysics. It is a convergence of observations and theory that is fundamentally changing how we think about the final years of massive stars. We are discovering that the death of a massive star is not a sudden event. It is the culmination of a process that may have been building for years, involving eruptions, mass loss, dramatic changes in luminosity and temperature, and the progressive disruption of the star's outer layers. The final explosion is, in some sense, the last act of a drama that has been playing out for a long time. The zombie was already walking before it finally fell. One of the most poignant and philosophically rich questions that this research raises is whether we can predict stellar death. Can we identify a massive star that is about to explode and watch it happen in real time? This is one of the holy grails of observational astrophysics, and the discovery of SN 2006 JC's pre-supernova outbursts suggests that at least some stars give warning signals in the final years before they die. The challenge is that identifying these warning signals requires monitoring enormous numbers of stars over long periods of time, because the signals are not obvious from a single observation. They require a baseline of previous observations to recognize that something has changed. This is exactly what surveys like the Rubin Observatory and the Zwicky Transient Facility are designed to do. By repeatedly imaging large areas of the sky and comparing each image to previous ones, they can detect changes in the brightness of individual stars, not just in nearby galaxies but across a large volume of the universe. If a massive star in a galaxy 10 million light-years away begins to brighten anomalously, if it undergoes an eruption like the 2004 outburst that preceded SN 2006 JC, there is a real possibility that this brightening will be detected. And if a follow-up campaign is mounted promptly, using spectroscopy and multi-wavelength observations, it may be possible to characterize the pre-explosion state of the star, watch the environment it is creating, and then catch the actual supernova explosion from the very first moment. This has never been done. Not once in the history of astronomy have we watched a star in another galaxy undergo a pre-explosion eruption, identified it as such, predicted that it would explode, and then watched the actual explosion occur. It has happened retroactively. Looking back at archival data after the supernova appeared, as with SN 2006 JC. But a prospective prediction and observation has not happened. The first time it does happen will be one of the landmark moments in the history of astrophysics. And with the new generation of surveys coming online, it is not just possible, it may be inevitable. We may be within a decade of watching a star die in real time, from the first eruption to the final explosion, in complete multi-wavelength detail. Imagine that. Imagine receiving an alert. It goes out over the astronomer's telegram, the rapid communication network used to announce time-sensitive astronomical discoveries, that a massive star in a nearby galaxy has undergone a major brightening event. Not a confirmed supernova. a brightening that looks like a pre-explosion outburst. Telescopes around the world, optical and radio and X-ray and infrared, turn to that galaxy. Spectra are taken within hours. The star is identified as a luminous hypergiant or a Wolf-Rayet star in its final stages of evolution, surrounded by dense circumstellar gas consistent with a recent major mass loss episode. The models are consulted. The predictions are made. This star, the models say, may explode within days to years. Nobody knows exactly when. And then you wait. The alerts keep coming. The star keeps brightening slightly and then fading. Months pass. A year passes. And then one morning, the alert comes that is different from all the others. The transient at that location has jumped in brightness by a factor of 1,000,000 overnight. The supernova has begun. That is a plausible scenario. It is not certain, but it is plausible. And if it happens, it will be the first time in human history that we have witnessed, from preparation to explosion, the death of a star. Not in our own galaxy, where the dust would likely obscure the optical view, but in a nearby neighbor, close enough to study in exquisite detail. The entire scientific and observational machinery of modern astronomy is, in a sense, being built toward this moment. The Rubin Observatory, the James Webb Space Telescope, the next generation of extremely large telescopes currently under construction, including the 30-meter telescope and the European Extremely Large Telescope. The Square Kilometer Array Radio Telescope. All of these instruments, working together, have the capability to capture stellar death at a level of detail that would have been literally unimaginable to astronomers a generation ago. And what would we learn? We would learn, for the first time, whether the pre-explosion behavior of massive stars is as dramatic and complex as the most extreme examples suggest, or whether those examples are outliers in a population that is mostly much calmer. We would learn whether the eruptions happen in a predictable sequence, a specific series of events leading up to the explosion, or whether the final years of a massive star are chaotic and unpredictable, defying any simple model. We would learn whether the circumstellar material that surrounds the star at the moment of explosion is structured in specific ways: rings, disks, irregular blobs, that can be mapped out by the interaction of the supernova ejecta and compared to the pre-explosion imaging. We would learn, in short, the full life story of a dying star, from pre-death throes to final explosion to young remnant, in one continuous, unbroken observational campaign. This is the frontier. This is the edge of what humanity can currently know about zombie stars, and it is receding outward at the speed of new observations and new instruments and new ideas. The scientists at that frontier are not working in isolation. They are connected globally, sharing data through electronic networks, coordinating observations across continents and hemispheres and wavelength ranges, debating interpretations at conferences and in papers and in the corridors of university physics departments. The discourse around zombie stars and superluminous supernovas and FBOTs and pulsational parent stability events is one of the most active and energetic in all of astrophysics, because it sits at the intersection of multiple fundamental questions. About stellar evolution, about compact objects, about chemical enrichment, about dark energy, about the habitability of the universe. To make progress on zombie stars is to make progress on all of these questions simultaneously. Let us now think about what all of this means in a broader, more philosophical sense. Because science at this level, science that grapples with events of incomprehensible scale, events that challenge our most fundamental assumptions about how the universe works, always has implications that go beyond the technical. It changes how we see ourselves in relation to the cosmos. It changes the story we tell about our place in the universe. We live on a small rocky planet orbiting a medium-sized star in a spiral arm of a large but not extraordinary galaxy in a universe that contains perhaps 2 trillion galaxies. Our entire civilization spans a tiny fraction of cosmic time. The events we have been discussing, supernovas, zombie stars, pulsational parent stability events, happen on timescales that dwarf anything in human experience. And yet we are able, through the extraordinary capacity of the human mind for abstraction and mathematics and observation, to understand these events, to build models of them. to detect them across billions of light-years of space with instruments made from silicon and glass and metal, controlled by algorithms running on silicon chips, all created by beings who evolved on a planet that owes its chemical richness to the deaths of stars billions of years ago. There is something almost unbearably poignant about that. We are made of stardust, and we have figured out the physics of the dust-making. We are the products of stellar death, and we have understood stellar death well enough to see it happening in real time across the universe. We are, in the deepest sense, the universe knowing itself. And the zombie stars, the stars that refuse to die, that erupt and survive and erupt again, that keep burning after they should have gone dark, are perhaps a mirror image of that. The universe does not give up easily. It does not follow simple rules. It finds ways to keep going, to keep burning, even past what should be the end. And in studying those stars, we are discovering something not just about astrophysics, but about the nature of persistence itself, about what it means to resist the final silence. Ask yourself this, genuinely ask yourself, is there something in the zombie star that speaks to something deeper? Not in a mystical sense, but in the sense of what it means that the universe, at every scale, contains mechanisms of resistance. Mechanisms by which the end is delayed, complicated, made impure. A star should die when its fuel is gone, but it keeps burning because of mechanisms. Pair instability, magnetar engines, CSM interaction, partial detonation, that the simple model did not account for. A neutron star should simply sit there cooling, but it spins and radiates and powers the supernova remnant from the inside. A white dwarf should simply explode completely in a type Ia supernova. But sometimes it does not. Sometimes it partially survives and haunts the remnant of its own explosion as a zombie white dwarf. At every scale, in every regime, the universe finds ways to be more complicated, more persistent, more resistant to simple endings than the simplest model predicts. Whether you take that as merely a statement of physical fact or as something with deeper resonance probably depends on who you are. For scientists, the complication is valuable precisely because it teaches us something we did not know. For others, there might be something more. Not literally. The stars are not conscious, not intentional, not fighting against death in any human sense. But as a metaphor, as an image, as a kind of story the universe is telling about its own nature, the zombie star has a power that goes beyond its scientific significance. It says, endings are not always simple. Death is not always final. The most violent destruction can coexist with ongoing creation. And the boundary between the two is often not a clear line, but a prolonged, complicated, luminous struggle. Now, let us return to the scientific for a moment, because there is one more class of phenomenon connected to zombie stars that we have not yet fully explored, and it is perhaps the strangest of all. It involves what happens when not one but two stellar remnants collide. When two neutron stars, orbiting each other in a tight binary system, gradually spiral together under the influence of gravitational wave emission, losing energy to the ripples they create in spacetime, and finally merge. The merger of two neutron stars is one of the most extreme physical events in the universe, and it was directly observed for the first time on August 17, 2017, in an event designated GW 170817. GW 170817 was detected first as a gravitational wave signal by the LIGO and Virgo detectors, a chirp in the fabric of spacetime, a signal lasting less than 2 minutes as the two neutron stars spiraled together at a significant fraction of the speed of light and then merged. 1.7 seconds after the end of the gravitational wave signal, a gamma-ray burst was detected by the Fermi and Integral Space Telescopes. A short gamma-ray burst, consistent with the theoretical prediction that neutron star mergers produce gamma-ray bursts through the formation of a rapidly accreting remnant. And then, in the days that followed, telescopes around the world detected an optical transient at the location of the merger, a kilonova, the radioactive glow of heavy elements freshly synthesized in the extreme conditions of the merger. Gold, platinum, uranium, and many other heavy elements were created in the fireball and scattered into space. For the first time, we watched the origin of gold. But what does the merger leave behind? The fate of the merger remnant. whether it forms a black hole immediately or collapses to a black hole only after a short-lived intermediate phase as a hypermassive neutron star, is one of the most important open questions connected to GW 170817 and future neutron star merger observations. If the combined mass of the two neutron stars exceeds a threshold, roughly 2.2 to 2.5 solar masses, depending on the nuclear equation of state, which is itself uncertain, the remnant will collapse to a black hole almost immediately after the merger. If the combined mass is just below that threshold, the remnant might be a rapidly spinning, highly magnetized neutron star, a magnetar, that survives for seconds to hours before collapsing to a black hole. And if the combined mass is even lower, the remnant might be a stable neutron star that survives indefinitely. The zombie star concept applies here too, in a fascinating way. If the neutron star merger remnant is a briefly surviving hypermassive neutron star before collapsing to a black hole, then for the brief period of its existence it is the most extreme version of the zombie phenomenon imaginable. A star that was already dead, that had already died in a supernova, that was already a neutron star remnant, that then survived the violent collision of two dead stars and briefly existed as something even more extreme before succumbing to gravity for the final time. The cascade of deaths, star to neutron star in supernova 1, star to neutron star in supernova 2, neutron stars to hypermassive neutron star in merger, hypermassive neutron star to black hole in collapse, represents 4 stages of stellar death in one system, each one more violent than the last, each one a form of resistance followed by surrender. The question of whether the GW 170817 merger remnant was a briefly surviving neutron star or collapsed immediately to a black hole is still being debated. The gravitational wave signal from the merger itself provides some constraints, and future detections of post-merger gravitational wave oscillations, the ringing of the hypermassive neutron star before it collapses, would provide detailed information about the nuclear equation of state and the fate of the remnant. But current detectors are not sensitive enough to detect this post-merger signal from the distance of GW 170817. The next generation of gravitational wave detectors, the Einstein Telescope, Cosmic Explorer, will have the sensitivity to detect these signals, potentially illuminating the final moments of the most extreme zombie stars of all. Let us also spend a moment with the concept of the failed supernova, a phenomenon that is almost the opposite of the zombie star in one sense, but deeply connected to it in another. A failed supernova, also called a collapsar or a direct collapse event, is what happens when a massive star collapses to form a black hole without producing a bright supernova. In this scenario, the stellar collapse does not produce a successful shock wave that propagates outward. Instead, the shock is completely swallowed along with everything else, and the star simply disappears, suddenly, without a visible explosion. What you observe from a distance is a star that was there and then is not there. Not a flash of light followed by a fading glow. Just an absence where there used to be presence. In 2009, a team led by Christopher Kohanek at The Ohio State University began the Large Binocular Telescope survey of nearby galaxies, designed specifically to look for failed supernovas, to search for massive stars that simply disappeared. They surveyed about 27 galaxies repeatedly over many years, cataloging hundreds of massive stars and watching for any that might vanish. In 2015, they reported what appeared to be the first candidate, a massive red supergiant star in the galaxy NGC 6946, a galaxy nicknamed the Fireworks Galaxy for its unusually high supernova rate that was luminous and well-studied, and then simply faded away in 2009. The star, designated N6946 BH1, brightened briefly in mid-2009. A brief luminosity increase that could correspond to the brief flash of a failed explosion or a final convulsive eruption, and then faded to levels consistent with no star being present at the location. Or at least, no star of the original luminosity. The subsequent interpretations have been complex. Later observations suggested the presence of some remaining infrared emission at the location, possibly consistent with a surviving dust-enshrouded object or with the faint infrared glow of fallback accretion onto the newly formed black hole. The situation remains ambiguous, and different groups have published different interpretations of the same data. It is possible that N6946 BH1 was a genuine failed supernova. a star that collapsed directly to a black hole. It is also possible that it underwent a major eruption, ejected a large amount of dust, and is now hidden behind a thick shell of that dust. Distinguishing between these scenarios requires more observations at wavelengths that can penetrate dust, and the search continues. The failed supernova is the dark twin of the zombie star, where the zombie star refuses to die, producing light long after it should have gone dark. The failed supernova refuses to explode, going dark without the expected blaze of glory. Both represent failures of the simple model, one by producing too much light, too persistently, and the other by producing almost no light at all. They are complementary pathologies of stellar death, bookends of the range of possible outcomes in the final moments of a massive star. And together they tell us that our textbook understanding of core collapse supernovas, the simple story of collapse, shock, explosion, remnant, is a simplification that captures the typical case but misses the fascinating extremes at both ends of the distribution. The fact that N6946 BH1 is in the fireworks galaxy is itself poignant. This galaxy, located about 22 million light-years from Earth in the constellation Cygnus, has hosted 10 observed supernovas in the past century, more than any other galaxy in the local universe, earning it the fireworks nickname. And yet among all those fireworks, there appears to be at least one star that chose not to explode, that chose the dark path, that disappeared without a light show. In the galaxy of fireworks, a silent implosion. Stepping back even further, we can now see the full landscape of what we have been exploring. Zombie stars are not a single phenomenon but a family of related phenomena. Different mechanisms, different progenitors, different outcomes, united by a common theme. The death of a star is not always what the simplest models predict. Stars can erupt and survive. Stars can erupt again and again. Stars can power their own explosions from the inside, using the energy of a spinning neutron star remnant. Stars can partially explode and partially survive. Stars can die in silence without the expected fireworks. Stars can die with fireworks that last for years instead of weeks. Stars can die in events so bright they outshine 100 billion suns. And in every case, the deviation from the simple model is a clue, a signal from the universe that there is something important we do not yet understand. And what we do not yet understand about zombie stars connects to some of the deepest questions in all of physics. The nature of dense nuclear matter, the equation of state of a neutron star, determines whether merging neutron stars form a stable remnant or collapse to a black hole. The mechanism of magnetar formation determines whether core collapse supernovas can power superluminous explosions. The physics of pair instability in very massive stars determines whether the first stars in the universe underwent repeated explosions and how they enriched the early universe with heavy elements. The mechanism of pre-supernova mass loss, why massive stars eject so much material in the final years of their lives, is connected to the physical processes of convection, rotation, and pulsation deep in the stellar interior that we still do not fully understand. These are not peripheral questions. They are central to how we understand the life cycle of matter in the universe. Every observation of a zombie star is a data point in the argument the universe is making about its own complexity. Every superluminous supernova is a demonstration that the most violent events in nature do not follow simple rules. Every IPTF-14 HLS is a challenge issued to theorists to come up with a model that works. And every time a theorist proposes a model and it almost works but not quite, that gap between the model and observation is itself a discovery. A discovery of what the model is missing, a discovery that points toward the next revision, the next improvement, the next step toward a deeper understanding. We are living in a golden age of zombie star astronomy. The observational tools available today, from ground-based surveys with robotic telescopes monitoring millions of galaxies every night, to space-based observatories studying the full electromagnetic spectrum, to gravitational wave detectors that can hear the vibrations of space-time itself, these represent a level of observational power that would have been incomprehensible to astronomers a generation ago. The data is coming in faster than the theoretical community can process it. New events are being discovered routinely. New classes of objects are being identified. New puzzles are being posed by the universe to the people who have dedicated their lives to reading its signals. And the people who do this work are remarkable. Saurabh Jha, studying zombie white dwarfs from Rutgers University. Yair Arkavi, making sense of IPTF-14 HLS from Tel Aviv University. Phil Tsigan and Claes Fransson and their collaborators, hunting for the neutron star inside SN 1987A with instruments in space. Anna Ho, systematically characterizing fast blue optical transients from Cornell. Subhwa Dong, discovering the most luminous supernova ever seen. Christopher Kohanek, patiently watching galaxies for stars that disappear. And dozens, hundreds of others whose names would take too long to list, spread across the globe, working in the dead of night in cold observatories in Chile and Hawaii and the American Southwest, or staring at computer screens running analysis code at 3 in the morning because the data came in and the deadline for the next telescope allocation is approaching, and there is something in this light curve that nobody has ever seen before and it needs to be understood. These are the people who are enlarging the human understanding of zombie stars. They are doing it one observation at a time, one paper at a time, one argument at a time in one conference session at a time. The process is slow and uncertain and sometimes frustrating, and it is also one of the most extraordinary intellectual enterprises in human history. We are a species that evolved on a small rocky planet around an unremarkable star, and we have developed the capacity to understand events happening billions of light years away, events that involve physics at temperatures and densities that exceed anything achievable in any laboratory on Earth. We have done this through mathematics and observation and the painstaking accumulation of knowledge across generations. It is, in its way, as extraordinary as the stars we study. Now let us look at one final mystery that brings the zombie star story to its most speculative and mind-bending extreme. It is a thought, a possibility, an idea that lives at the outermost edge of current theoretical thinking, and it involves the concept of a star that does not just refuse to die but achieves a kind of permanent survival through the most extreme physical mechanism imaginable. We know that the most massive stars can produce parent stability supernovas, events in which the entire star is disrupted and no remnant is left behind. But there is a theoretical window of mass, roughly between 100 and 130 solar masses, where pulsational parent stability events occur repeatedly without necessarily destroying the star completely, and where the final fate depends sensitively on the initial mass and composition. Some models predict that stars near the upper end of this range will undergo a pulsational parent stability sequence that ejects enough mass to bring the remaining core below the threshold for parent stability, at which point the core collapses in a normal core collapse supernova, leaving a neutron star. But some models predict that the pulsations themselves can be so energetic and so efficient at ejecting mass that the remaining core becomes too small even to undergo a standard core collapse supernova, that it might instead collapse quietly to a black hole, like a failed supernova. And then there are models that predict even stranger outcomes. One such theoretical possibility, and I want to be very clear that this is at the extreme speculative frontier, not mainstream consensus, but it is based on real physics, involves a massive star that undergoes pulsational parent stability events, ejects mass each time, contracts, and then at some point reaches a state where the remaining stellar structure is stable against further collapse. This would be a star that has found, through a series of violent eruptions, a new equilibrium, a post-pulsation state in which the physical conditions no longer favor either parent stability or core collapse. In this scenario, and I emphasize, this is theoretical speculation, not established fact, the star could potentially persist in this modified state for an extended period, essentially having survived its own destruction multiple times and arrived at a configuration that resists further death. We have no observational example of such an object. If it exists, it would be extremely rare and might be difficult to identify because it would not look like anything we have previously classified. It might look like a highly unusual, chemically peculiar massive star in an advanced stage of evolution, surrounded by multiple shells of ejected material, with an unusual spectrum reflecting the products of advanced nucleosynthesis in its interior. Eta Carinae has been proposed as a possible candidate for such an object, a star that has, perhaps, been managing its own instability through repeated eruptions for so long that it has carved out a kind of prolonged existence despite the physics that should have killed it. This is speculative, but it is the kind of speculation that, if true, would mean the universe contains objects that are in some sense permanently compromised between living and dying, perpetual zombies not in the sense of erupting and recovering but in the sense of perpetually occupying the knife edge between stability and destruction. Is there a limit to how long such an object could persist? Is there a path by which a pulsating massive star could delay its inevitable death indefinitely, or only for a finite additional time? These are questions that current theory cannot definitively answer, because the long-term behavior of these objects depends on physics that is not yet fully understood. The nuclear burning rates, the convective transport of energy, the structure of the envelope in the post-pulsation state. All of these involve uncertainties that translate into uncertainties about the timeline. But all the physical intuition we have says that the delay can only be temporary. Gravity always wins in the end. The fuel always runs out. The star cannot keep exploding forever. It will eventually reach a state from which no recovery is possible, and then it will die for real. Finally, irreversibly, with a completeness that all the previous eruptions only postpone. And that, perhaps, is the deepest truth that zombie stars reveal about the universe. Not that stars can avoid death. They cannot. Not that the physical laws can be suspended. They cannot be. But that between the birth of a massive star and its final death, there is a space of time, sometimes very long, in which the star can refuse the simplest version of its fate, in which the physics can produce, not a clean ending, but a prolonged, complicated, violently luminous middle chapter between life and final death. That middle chapter, the eruptions, the survivals, the re-eruptions, the interaction of explosion with previous explosions, the spinning magnetar keeping the remnant lit, the partially destroyed white dwarf haunting the remnant of its own explosion, that is the domain of zombie stars. And it is one of the most physically rich and observationally exciting domains in all of astrophysics. The next time you look up at the night sky, if you are somewhere dark enough to see the stars clearly, look at the bright ones. The really bright ones, the ones that shine with a steady, unblinking light in the southern constellation Carina or Scorpius or Orion.